learned about drift velocity. Okay, so what is drift velocity? Let's say we have a conductor. Now, when I say conductor, you can think of it like our wire, okay, our copper wire. And then metal, all metal, they have free electrons, right? Delocalized electrons. And these electrons, they are free to move around the structure, inside the structure of the metal. How fast they move? Very fast, a few hundred kilometers per second. It's very fast. That motion is due to the thermal velocity. We call it thermal velocity is because that motion is contributed by heat. Okay, any object at a given temperature. Okay, we have person logging in. Let me just click. Okay. If you take a material at any temperature, as long as it is not at absolute zero, all the electrons, they move very fast inside. All the atoms, the ions in the structure, they move very fast. At absolute zero, then everything would be at rest, okay, not moving. But as long as there's 1 degree, there's temperature, then all the atoms, they are moving. That velocity, that motion, we say it is the thermal velocity of the ions. Okay. Now, in any given second, let's say we take 3 electrons in any given second. Let's say the first one go here. This is the velocity vector of the electron. Another one go here. Another one go here. Now, when there's no potential difference, okay, no potential difference, then it would just continue to move in whatever direction that it is currently moving. Okay, and they don't move in straight line, they move in zigzag because they bounces off of one another and they bounces off of the positive ion. So they go in a zigzag direction. The net velocity, they will cancel out. So that means there is no net flow of electron. Okay, this velocity with this one, they cancel out the effect. Okay, so overall, we can say that the electron is not flowing. Right? They are moving, but they are not flowing in one direction. Now, when I apply a potential, positive, I connect to a battery, positive, negative. Okay, so electron negatively charged. When there's an electric field, it will be attracted to the positive terminal to the left. So they will start to drift. You see, this is the original velocity. With the potential, they go like this. Okay, from this point to this point. Take a very small vector. Same for here, this one. This vector, this is the original vector without the potential. If you apply the potential, then it goes here. Okay, now the change, again, from here, go to here. A very small vector. All this happens to every single electron. Okay, this electron is currently going here, and potential, it goes slightly to the left. Okay, now all this small velocity, we say it the drift. Okay, because the electron is drifted towards the left side. Every single electron has this velocity. It's a very, very small motion, we are talking about millimeter per second. Okay, millimeter per second, very small motion. But it happens to every single electron. Okay, now if it happens to every single electron, then every electron in 1 second, they move slightly towards the left. Okay, now all this, if you take the average of this velocity, let's say you take the first electron, V1, you plus the velocity of the second electron, plus the third one, plus how many electrons are there in the metal, you divide by the number of electrons, you get the average. Okay, the average of all this, and this average velocity is drift velocity. Okay, so what is drift velocity again? It is the average velocity. Okay, the average velocity of the electron when a potential difference is applied. Okay, now We want to know the relation of the drift velocity with the current. What is the relation with this and the current? Because in physics, it's all about measurement. Everything that we define, we need to be able to measure it. So that means we need a formula relating the drift velocity with the current. Okay, let's start with this. Here we have a conductor. The same conductor here. And we are going to take 2 points. This first point and this one. Consider the electron started from here, moving at a velocity v to the right. Okay, so that's the drift velocity. But here, it traveled a certain distance, d, in a given time, t. Now, using the speed, distance, time, so we can write velocity equals to displacement over time. And we adjust it a bit, d equals to vt. Okay, so that's the distance. Now, if I want to get the volume of this part, the middle part, okay, I would take the cross-sectional area times by the length, which is d, so AD. Okay, now d, I just put this one in here. I get AVT, that's the volume. And from here, I can find the total number of electrons. Okay, you see, if I want to find the total number of electron moving in this volume here, then I would take the volume, which is AVT, times by a physical quantity that we call the electron density. Okay, we denote it as N. Okay, what is N here? Again, N is the number of electron per unit volume. Okay, number of electron per unit volume. That means in 1 unit volume, 1 meter cube or 1 cm cube, how many electrons are there? That depends, of course, depends on the material. If you're talking about copper, okay, maybe has less than silver, depending on the material. Some material, they have more free electrons, okay, especially the good conductors. So this N really depends on the material, okay, how many electrons in 1 unit volume. So if I want to find the total number of electron, then I would take, you see this one AVT, what is this? This is the volume, right? Then I just times how many electron in 1 unit volume. Then I get the number of electrons. Okay, so AVT, and now I get the total number of electrons moving in this region in a specific time, and then I can find the total charge. Total charge. Number of electrons times the charge of 1 electron. So AVT, and charge of 1 electron is 1.6 times 10 minus 19. I'll just call it E. Okay, so I put E here. I get the total charge flowing. Okay, I get a total charge flowing in a given time. Okay, now current is total charge flowing in a given amount of time. So I equals to Q over T, Coulomb over second. So I put this one, Q, total charge, I put it in. A, V, T, and E divided by T. So cut, I get A and EV, NF, I. This is your equation. Okay, I equals to A and EV. You need 2. One is this one. One is this one. You're going to need it to for the calculation. So which one is drift? What is drift velocity? If they want you to find the drift velocity, then you just do this one move here, I, A, and E here. Okay, so this V here is our drift velocity. What is drift velocity? It is an average. Okay, it's never just one. is an average velocity of every single electron that is supplied, that is influenced by an electric field. Yeah. Now, current is the flow of charge. Now we look at why charges flow in the first place. What makes charge to flow? It is the potential difference that causes charges to flow from one place to another place. Now, the best way to think about it is like this. Here we have a positive charge. Conventional current is the direction of where the positive charge flow. Okay, so if electron is going to the right, current is flowing to the left, is opposite to the electron flow. Now, here I would just assume that there is a positive charge, okay, same direction as the current. We have a positive charge flowing from one place to another place, from left to right. Here we look at why should it flow in the first place? Because there is a potential difference created. Let's say I put here positive charge, and then here is negative. Okay. Now, when I put a test charge in it, the charge will move, repel positive, it will move to the right. Here, this is the natural, we say that this is the natural motion of the object, because when I place it, immediately it repels. That is the natural motion. Whenever object move in natural motion, the potential energy decreases. Okay, remember this one. Whenever object move in natural motion, their potential energy decreases. Just like I drop an object from a certain height. I let go, it moves down. That is the natural motion. So as it moves down, potential energy decreases. That is the gravitational potential. For this one, when I put a charge here, the charge repels and goes here. This is the natural motion. So whenever it goes in natural motion, the potential energy decreases. What potential energy? Electric potential energy in this case. Okay, so potential energy is like a stored energy. Stored energy. You can think of it like when I put the charge here, it has stored energy, so it can do work. Right? It has stored energy, so it can do work. How does it do work? By moving to the right. As it gets here, then no more motion because it's already done certain work, and this work equals to the amount of stored energy inside. Yeah. Now, take this concept and relate with our potential difference. You see, when the charge moves from left to right, let's take 2 points, point A and point B. Which point has higher potential energy? Point A has higher, point B has lower potential energy. So since point A is higher potential energy, then we would say that that location is higher potential. This is a higher potential location, and this is a lower potential. Okay, so higher potential is always the positive terminal. Lower potential is the negative terminal. So current flow from positive to negative, from higher potential to lower potential. And as it flows, the potential energy of the charges decreases because that is the natural motion. Okay, so it is the potential difference that causes charge to flow. Potential difference, you can imagine like high ground and low ground. By creating a potential difference, I create a high ground and I create a low ground. Okay, so objects flow from high ground to low ground. Object cannot flow from low ground to high ground unless there's external force applied. You push the object, you raise the object from low ground to high ground. That is when external work is done. But by naturally, object cannot flow from low ground to high ground. The same concept for this. If I have two water tank is connected like this. Let's say the two water tank, I fill it with water like this. Okay, how do I move all this water in container B to container A without adding or removing the water? I can just adjust the position, but I cannot add any water. How do I move this water? I have to raise container B. Okay, I have to raise container B so that it goes something like this. Okay, so like this. Okay, so container B is lifted up so the water can flow from B to A. Now what I'm doing here, I'm creating a high ground, again high ground and low ground. So the high ground, low ground causes the water to flow from B to A. Again, there's a height difference, right? There's a height difference. In this case, we call it height difference. But in the case of electricity, the battery, the potential difference is the height difference. The battery is the one that creating this high ground and low ground so that the charge can flow. Right? So is potential difference a force? No, it is not a force. Okay, it is a location where the energy is different. Okay, high ground and low ground. Now, you see, the battery has two terminals, positive, negative. At the positive terminal, it's all high potential. So all the charges stand by here. They have high stored energy, but they cannot go anywhere because there's no path, right? But the moment you create a path, you put a wire connect to the negative, you have created a potential difference. By joining the high potential to the low potential, you have created a path for the charge to flow. So the charge will take the path because there is potential difference. If I reverse this terminal, if I take this terminal as positive, like this, can the charge flow? Like this? Cannot. Why? Because positive is high potential. So you have high potential at the left and high potential at the right. It's the same potential, so there's no flow. Okay, same potential, there's no flowing. Same potential is like this water tank here. They are at the same height. The water cannot flow from left to right, nor from the right to the left. Okay, you must create a difference in potential like this one for the charge to flow. Okay, now let me erase this on the left first. Okay, so we have a circuit here connected with resistors. Location of positive has higher potential. So over here has higher potential. As the charge flow from positive to minus, their energy decrease, right? So natural motion, potential energy decrease. Where does the potential energy go? Potential energy is being converted to other forms of energy. Where is it being converted? At the resistor, R1, R2, R3. At this resistor is where the energy conversion happens. So electrical energy got transferred to heat energy. So the resistor heat up. Okay, because conservation of energy, when potential decrease, something has to increase. The heat energy increase in this case. So the energy conversion, we would call it the potential drop. As charge move from one point before the resistor and cross the resistor, there is a potential drop. Okay, a potential drop. Again, run through this R2, again, there's another potential drop. Through R3, there's another potential drop. And by the time it reached the negative, What is the potential? The potential becomes zero. Zero. If I say that the battery is 3 volt, at the positive, the potential is 3 volt. And by the time it reaches the negative, it becomes 0 volt. Because there's a potential drop here, 1 volt, 1 volt, 1 volt, no more. Considering the resistance has the wire has 0 resistance. Okay, if the wire has resistance, then again, when current flow through the wire, there is also potential drop. Later, I will show you one example of that. But here we would assume that the resistance of the wire is negligible. Okay, so that means every time the charge flow, there's a potential drop, potential drop. So where is high potential region? The closer the point is to the positive charge, the positive terminal, the higher will be the potential. Compare potential over here. What is the potential over here? B. Okay, A. Point B, point C. Which point has the highest potential? The closer to the positive terminal, the higher the potential. So point C will have the highest potential, point B, and then last is point A. What about if I take point D over here? B and D, which one has higher potential? Negligible wire resistance. So here, when the current flow from B to D, there's no potential drop. That means B and D is the same potential. Okay, so same potential. When you connect your voltmeter here, what happened? You do not get any reading because there's no potential difference. It's the same. There's no potential drop happening between B and D. But if you connect your voltmeter from here, A, across this, D, to D here, there is a potential drop in the middle, so you will get a reading. D is bigger than A, and you read whatever the potential drop over here. Okay, here. Now, potential difference. What does it mean by 3 volt again? Potential difference. Conceptually, potential difference is the high ground and low ground, right? But if you want to define it, define potential difference, we cannot say it's high ground and low ground because we want something that we can measure. So something that we can measure, okay, you see, potential difference is the drop in the energy. What is energy? Energy is work done. Work done, can we measure? Yes, we can measure work done. So we define potential difference as work done. Okay, the high ground and the low ground causes the charge to move, and when the charge move, they do work. Right? Let's say here, C and point E. High ground at C, low ground at E. Charge move from C to E. There's work done. So we define the potential difference between C and E is the work done for the charge to move from C to E. Okay, work done for the charge to move from C to E. Let me write it down here. Oops. Okay, so potential difference is defined as work done by 1 coulomb of charge. Okay, from one point to another. Potential difference between 2 points is defined as the work done by 1 coulomb of charge. Okay, we take 1 coulomb of charge from one point to another point. Any 2 points in the electric field, in the wire, in the circuit. What is potential difference between D and A? Okay, D and A here, okay, it is the work done for the charge to go from D to A. Why the charge is doing work? Because of the potential difference. So that's why we use work done as the definition. Okay, or you can also say Potential difference is the amount of electrical energy converted to heat energy. Because as it do work from D to A, there's energy being converted, and the energy is equal to the work. Energy also we can measure. So another way you define it, you can say potential difference is the amount of electrical energy being converted to heat or other form of energy when they move from D to A, when they move from point D to point A. Yeah, so V potential difference equals to work done divided by 1 coulomb of charge, so divide by Q. Again, this is the second, another formula that you need to know. W is joule, C, coulomb. Okay, so if I say that the battery is 3 volt, what does it mean? That means the battery is giving 3 joule per 1 coulomb. Okay, imagine like you have 1 coulomb of charge here. How much is 1 coulomb? About 6 times 10 power of 28 electrons, trillions and trillions of electrons in just 1 coulomb. If I say that the battery is 3 volt, that means it is giving 3 joule per 1 coulomb. When it gives this much of energy to the charge, then the charge take the energy and they go around the circuit, they use up the energy by the time they reach the negative terminal. Okay, so this one, 1 volt, that means it consumes 1 joule per coulomb. Another 1 volt, it consumes 1 joule per coulomb. This one, 1 joule per coulomb. Total, how many joule? 3 joule per coulomb. So the battery supply 3 joule per coulomb, but when the charge go through the external circuit, it use up again the 3 joule per coulomb. So when it reach negative 0, and again it pass through the battery, gain again 3 joule per coulomb, and again it loses the energy as it flow in the external. So there are 2 types of circuit: internal circuit and external circuit. External circuit is the wiring. Okay, the wiring connecting the positive terminal to the negative terminal. Internal circuit is inside the battery. The internal circuit is supplying the energy. The external circuit is converting the energy into other forms with the help of the resistor. Yeah, so that is potential difference. Now, potential difference is, again, work done between 2 points. Now, what is the difference from EMF? Electromotive force. Okay. They are very similar, but not exactly the same. The definition for EMF and electromotive force is the same. Okay. Now, let me erase this first. I hope they have a bigger eraser for this. Maybe they should update. Okay, so let's draw the circuit. Let me here. One here. Okay. Oops. All right. So potential difference at any 2 points. Let's say I can calculate, if I take this point A and this point B, calculate the work done, then I get potential energy between A, B. If I take this point C, this point D, calculate the work done over here, then I get potential energy between CD. What if I take at the terminal? If my 2 points, I take one here, E, one is here, F. Then this is, again, we call the potential difference between E and F. But since E and F is at the terminal, then we will call this terminal potential difference. Okay, terminal potential difference. So terminal potential difference is the potential difference between 2 points at the terminal. So for example, if I say that terminal potential difference is 9 volt, again, what does it mean? It means that the charge is doing, what is the definition of potential difference again? Work done by the charge. So that means 9 volt that means the charge is doing 9 joule of work when it moves from E to F, from positive to the negative terminal. It is doing 9 joule of work per coulomb, okay, per coulomb. So imagine we have 1 coulomb of charge here, 9 joule from here, moving from here to here. What about full cycle? This is just from terminal to terminal. What about if the charge moves 1 complete cycle? Is it full cycle? This is not full cycle yet because we cannot see what's inside the battery. The charge, there is still a small distance inside the battery. The charge reach the negative, they can also move from negative to the positive in the internal circuit over here. This amount of distance, this very, very small distance, but there's a resistance in that distance. There's a resistance inside the battery. The charge is doing 9 joule moving from E to F, and then as it complete the circuit, maybe it do a little bit of energy again, moving from negative to positive inside the battery, 1 joule. So the total amount of energy done by the charge, how much? It is not 9 joule. It is not 9 joule. How much? It is 10 joule. 9 plus 1 joule equals to 10 joule. 10 joule of work the charge is doing when it goes 1 full cycle. So if the charge is doing 10 joule of work, who is giving the charge this energy? Because to do work, you need energy, right? Who is giving the charge this 10 joule of energy? The battery is supplying this 10 joule. Okay, is the battery supplying 9? No, it's 10. But this 1 joule we cannot see because we cannot see what's inside the battery. We only see 9. When we put the voltmeter, we measure, we only get 9. We cannot see the 1. But the battery is not supplying 9. It is supplying 10. Okay, so 10 joule, the amount of energy that the battery supply is the EMF. That is the difference between EMF and the terminal potential difference. 10 joule per coulomb. What is it? 10 volt. Okay, the battery supplying 10 volts, and this is the electromotive force. Electromotive force. When you take a battery, you buy a battery, in the packaging it says 10V, let's say 10V. That is the EMF. Okay, that is the EMF. Whatever written on the packaging, that is the EMF. That is the total supplied by the battery. But as you take out the battery and then you put it, you measure, you put the voltmeter, you put the wire at the positive terminal and then the negative terminal, you measure the voltmeter. What are you measuring? You are measuring what? You put it at the terminal. So that is the terminal potential difference. So when you take a voltmeter, you measure, you won't get 10 because there's internal resistance. Maybe you get very close to 10, but still it won't be exactly 10. Okay, so when you take measurements, as long as you take measurement, you are always getting the potential difference terminal. You cannot get the EMF. How do you get the EMF? You have to you have to do graph, you have to do experiment, you get a bunch of values, you get the graph, and then from the graph only you calculate what is the EMF, that is the real power supply for the battery. Okay, as long as you are measuring, you always get the PD because there is internal resistance. Okay, so electromotive force, again, how you define it? Electromotive force, now let me write it here. It is defined as work done is the same as potential difference. We are also talking about work done by 1 coulomb of charge passing through 1 complete cycle. The keyword is here, 1 complete cycle. This is what? From one point to another. Potential difference is from one point to another. EMF is 1 complete path. So if I say, what is the EMF between C and D? That is a wrong question. Because EMF must be 1 complete cycle. I should say, what is the potential between point C and point D? Okay, 2 points, any 2 points on the circuit. Right? Now, why you cannot straight away measure like this? 10V, this is the battery, EMF is 10V. And when you connect to a circuit, straight away you become 9V. Where is the 1V? The 1V is this one, the work done by the charge inside the battery. This work done, this 1 joule per coulomb, we call it the lost volts. Okay, lost volts. The lost volts. Okay, so EMF is 10. Terminal potential difference is 9. And the lost volt is 1. These three, I can form an equation. EMF equals to terminal potential difference plus lost volt. You see, EMF is 10 equals to terminal potential difference is 9 plus the lost volt is 1. So you get this equation, E equals to VT plus V loss. Okay, what is the V? You learn V equals to IR, so you just put it inside. E equals to IR plus IR. The V loss is due to the resistance inside the battery, so we use a different symbol, small r. We get this equation, EIR plus IR. What is the big R? The big R is the effective resistance of the circuit. Here, 2 ohm, 2 ohm, 2 ohm. What is the effective resistance? 2 plus 2 plus 2. Series circuit, you just add it up. So 6 ohm. Do you add the internal resistance 1 ohm here inside? You do not add that. You do not add that. You only add the resistance outside, not inside the battery. That is your big R. Okay, that is your big R, resistance effective. Okay, now, so far we have looked at current, potential difference, and EMF. EMF, okay, the definition, in the past years, they always ask the definition also. So another way to define the EMF is sometimes you see they write it like, instead of talking about the work done by 1 coulomb of charge passing through 1 complete cycle, they also can define it as the amount of chemical energy being converted to electrical energy. Okay, because the energy supplied by the battery, the total, comes from the chemical, okay, chemical energy into the electrical energy. Okay. Okay, now next part we will look at resistance, and the resistance of, let me clear this. Take a uniform wire and let's say it's copper. Here, when current flow through the length of the wire, okay, a uniform wire with a certain length L and a cross-sectional area A and a resistivity of, okay, whatever value it is, I think it's 1.7 times 10 minus 8 ohm meter. Okay, so copper has a very low resistivity. That's why it is a good conductor. But if you compare, there are materials that high resistivity, such as the tungsten, okay, or the nichrome wire. They have high resistivity, means that they have high resistance. So when current flow through it, they convert a lot of the current into heat. Okay, so usually the heating material, the heating element, they use like nichrome. Okay, all these materials like the electric kettle, the heating element inside. Okay, they use high resistivity material. But for wires, okay, we want as low as possible lah. We use copper, more common, we use copper. Silver has a smaller resistivity than copper, but because silver is very expensive, okay, so that we use copper more. Okay, so R for the resistance, let's say we have current flowing in a certain length and in a certain cross-sectional area. So the resistance of this wire can be expressed as rho, okay, L over A, the resistivity times the length over A. Now for the same material, the relationship between L and A, R is directly proportional to L. The longer the length of the wire, the higher will be the resistance, and R inversely to the A. The cross-sectional area, the bigger is the cross-sectional area, okay, you can think of it like wide or narrow, the less the resistance. Why? Because if the cross-sectional area is very large, then that means there are more room for the electron to flow. Okay, there are more room for the electron to flow. If the wire is very narrow, then it's very difficult for the electron to flow, because they would just like rub against each other, and with the wall of the wire also bounce off of each other. Okay, more room, easier to flow. So that's why cross-sectional area increase, then resistance will decrease. And sometimes they ask for the diameter as well. Okay, so this is 1, this is 2. We can also express in terms of the diameter. So area of the cylindrical shape would be pi r square h, sorry, not cross-sectional area, pi r square. Okay, pi r square. So r equals to diameter divided by 2. R square would be d square over 4. So pi d square over 4. That's our area. So we put it inside. R is directly proportional to 1 over pi d square over 4. So R is 4 over pi d square. We drop the constant, drop this. So this one become 1 over d square. 3 relationship. One with the length, another one with the area, and also with the diameter. You can see the d square here. So if I double the diameter, you have a square. You double, become 4. So the r will be reduced by 1/4 if I just double the diameter of the wire. Okay, and also about resistivity. Resistivity, the unit. Okay, if you do resistivity Ra/L, we change all this into unit, you get ohm, area is m square, length is m. Cut off, we got ohm meter. Okay, so the unit of resistivity is in ohm meter. What is resistivity again? It is the resistance of a conductor if we take it as 1 meter square and 1 meter length, 1 meter square area and 1 meter length. Okay, if I say that the resistance of the resistivity of silver, say 1.6 times 10 minus 8 ohm meter. So that is the resistance of a wire of 1 meter square cross-sectional area and 1 meter length. Okay, this is that much of resistance. Okay, so because of the property of resistivity, because different material, they have different resistivity, so they are used in making resistor. So we have resistor, let's say we have a resistor that is made of nichrome. Okay, that I shape it like this. Okay, suppose that nichrome is used to make a thin film resistor, like a rectangular shape like this. So this is the cross-sectional area with the length of 15 cm, let's say with a thickness of 1 millimeter, 1 cm. Okay, now calculate the resistance of this thing, of this component. Again, we can use R equals to rho L over A. Given the resistivity of nichrome is 1 times 10 minus 6 ohm meter. Okay, so 1 times 10 minus 6 times 0.15 divided by cross-sectional area. Okay, cross-sectional area is this one. In this case, it is a rectangular cross-sectional area. So we just take 1 cm times this. Okay, so 1 times 10 minus 2 times 1 times 10 minus 3 equals 0.015 ohm. Okay, another example. Oftentimes also they will ask, okay, a resistance of wire, let's say we have a wire with a certain length and radius R, they give all bunch of unknowns, L, R, and then resistivity like this. It says that, okay, it carries a current I. Now, another wire of length 3L, radius 2R, and resistivity of 2 times the resistivity of this one. Both are connected to the same potential difference. What is the current flowing here? Okay, again, it is the algebra questions. So we start off with current equals to V over R, because they are connected to the same potential difference, right? So we can drop this I proportional to 1 over R. Okay, but we want in terms of all these parameters, the L, R, and resistivity. Okay, then we expand this R since we know R equals to rho L over A. Okay, so I can write this as I. Okay, let me do like this first. Let me sub in the equations equals to AV over rho L. Okay, so A expanded pi R square V over rho L. Then only I drop the V, I proportional to R square over rho L. Okay, drop the two constant. So R square over rho L. This is the relationship. Then we do I equals to R square over rho L, equation 1. And equation 2, that is what we want to find, I2 equals to, okay, put in the parameters, 2R square over 2 rho times 3L. Four R square, 6 rho L. Okay, so this one is equation 1. So I2 equals to I 4 over 6. Okay, 224, 236. So that's 2 over 3I. Okay. Now for the resistance of a component, they always combine with the power. Like they ask for, okay, what is the resistance of this wire here? And then they ask for what is the power dissipated, calculate the power or the current drawn. Okay, so when talking about power, recalling back the equations for power, what do we have? Equations of power. Let me just clear this up. P equals to IV. Okay, so Ohm's law, VIR, we get P equals to I square we get, substituting this one, we get P equals to I square R and P equals to V square over R. So this one and this one. This two is used to calculate power dissipate or power loss. Okay, because you can see these two, both equation has resistance, right? Both has resistance. So it allows you to calculate the power loss across a resistor. Across a resistor. Okay, for example, now sometimes you will often see that they put, like, they give you a resistor. Okay, let's say we have a resistor, and this resistor is used to make a heating element of a device, and they say that this resistor has a label. It is labeled as 20V 10 watt. What does it mean by this thing? Label 20V 10 watt. This means, okay, this means when you connect 20 volt power supply to this resistor. Okay, it will operate normally. Okay, the normal operating voltage, let me write it down. Normal operating voltage is at 20 volt. And when you connect 20 volt, if it's allowed to operate normally, then it would consume a power of 10 watt. Okay, it consumes 10 watt. What is 10 watt? 10 watt is 10 joule per second. So when you give it 20 volt, then every second this resistor, it will consume 10 joule. It will consume 10 joule. Convert this 10 joule of electrical into heat. This is what it means by the label. But in other conditions, if I give it other voltages, 15 volt, not 20, okay, then the power is no longer 10. This is only under normal conditions. Okay, so if you connect it, it depends on the connection as well. Normally, we use a series connection. Okay, we use a series connection for the heating element, all these heavy devices that needs high power to operate. But if you connect into parallel circuit, and sometimes they do not get the voltage that they are supposed to get. Okay, they get lower voltages, so they are not operating at their optimum condition. Okay, so let's say we have a resistor here labeled 20V 10 volt. Okay, then the question asks you, all right, calculate the current flowing in the resistor, I. Okay, so we have V equals to 20V, power equals to 10 watt. Calculate the current, so we can do P equals IV equals to power 10 equals to I 20. So I equals to 0.5 ampere. This is the current drawn. When you connect 20 volt, then it will draw 0.5 ampere from the circuit. And then calculate the resistance. Okay. A is current. B. Calculate the resistance of the resistor. Then we do, okay, P equals to V square over R. Power equals to V square over R. So R equals to V square over P. 20 square over power is 10. Okay, equals to 40 ohm. Okay, you can also use P equals to I square R. Since you already got the current, so 0.5 square times the resistance. Oops, this one should be R equals to P over I square 10 over 0.5 square. So still get the same 40 ohm. Now, this resistor, once you get the resistance of the heating element, depending on the element, okay, usually it's a fixed resistor, doesn't change. Okay, the resistance of a metallic conductor doesn't change. So if you do the VI graph, it will be a straight line like this, doesn't change. But for filament bulb, okay, filament bulb or diode, their graph is a bit different, right? Filament bulb, you get the curved graph. That means the resistance changes. Okay, the resistance changes depending on the temperature. Okay, now suppose that, okay, I take this heating element, I take this resistor, and I go and make a circuit. Okay, here. I connect the resistor with two cables with the resistance of 2 ohm each, 2 ohm, 2 ohm. So this is my 20 volt, 10 watt. Let me read the label resistance. It's 40 ohm. Okay, so I take two wires of certain length and I connect like this to a power supply with an unknown node, with a certain voltage, that I make sure that this voltage is adjusted so that this one can operate normally. Okay, operate normally. A, calculate the voltage of the supply. Okay, let's do voltage of cable first. The voltage of cables. Okay, we have the cables, we cannot ignore the resistance. So 2 ohm each. Now we want to find what? The voltage, the potential drop, right? Remember when going through resistance, cable with resistance, there is a potential drop also. Okay, yeah? So what we want to calculate that voltage of cables. Okay, then you do VIR. Since you already know the resistance, and also when you connect this, we already calculated before here, it will draw how much current? It will draw 0.5 ampere current. Okay, so it draws 0.5 ampere current. So you have the current, you have the resistance, V. Okay, V equals to 0.5 times 2. Okay, I'll just do in total because we got this one here, we got this one here. So I just put in total 2 volt. 1 volt each. Okay, 1 volt each. B, calculate total voltage supply. Total voltage supply. Okay, then we add up. Here we got 1 volt, here got 1 volt, and plus the voltage across the resistor as well. Okay, 20 volt. So 1 plus 1 plus 20, 2 volt. C, calculate the power dissipated in the cable. Okay, so we know the resistance. Power dissipated can do P equals to V square. V square over R. Okay, anything that any one of it you can use because you already have the current as well. All right. So if I use, let's say, using this one. So now you want to be careful when you use this one. The V is which V? The V is not the total voltage supply, because you're calculating the power loss across the cable. So this V is the voltage across the cable, not the voltage of the power supply, and also not the voltage of the resistor. Okay, so PV is 2 square. The voltage across the cable divided by the resistance of the cable equals to 1 volt, 1 watt. Okay, because this is a series circuit, the voltage is different for each component. This one V here, different than the V over here, than the V over here. So you have to be careful when you use this formula here, the V square. Or you can use P equals to I square R. Now in this case, the I is the same for everybody. Okay, because we have a series circuit, so I is the same for everybody. P equals to I square R, and then we can do 0.5 square over times with 4. Again, you get 1 watt. If you get conversely, if you get like a parallel circuit, you want to be careful when you use this formula to calculate the power loss of the component. Okay, let's say I want to calculate the power loss of component R1. When I use this formula, P equals I square R, what is the current? The current is not the total current, okay? Not the total current. It is the current flowing through the R1 in case of a parallel circuit. Okay? For a parallel circuit, if you use P equals to V squared over R, then you do not worry because the V is the same everywhere. Okay, so this is just a short one on the power calculation, power dissipation calculation. Now, I have already prepared a exercises